So we did the torque was the angular counterpart to the force, and now we need to do that the moment of inertia is the angular counterpart to the mass. Okay. Okay. So for the moment of inertia, this is the angular counterpart to the mass, such that, now let's see, the thing is that we talk about mass in two different ways, right? That matter is made out of atoms that are held in place by electromagnetic bonds, and that the atoms were made out of the protons, neutrons, and electrons, and that those electrons had a characteristic mass, right? And so each of the particles essentially have a characteristic mass. And so the more particles you have in the object, then the more mass the object has. So that was one option. And I like that because I think it's pretty visual. It's a pretty nice model. However, we could also talk about the fact that mass was the measure of the inertia of the object. And we talk about that as being the ability to resist changes in its state of motion, the ability to resist being accelerated. And we talk about the little car and the big truck, like in the parking lot, right? If we apply the same net force to both, the little car has a pretty good acceleration, the big truck, not so much. If you want both the car and the truck to have the same acceleration, you will need more net force on the truck because it has more mass. It has a greater ability to resist being accelerated or changing its state of motion. Okay. And so that's the one that counts. And you can see because it has the inertia in the name, right? That was the inertia. Such that, it indicates the ability of an object to resist changes in its angular motion. We change the angular motion of an object, then really what we're doing is we are angularly accelerating. And so then what I like to do is I like to kind of picture just this isn't really a derivation, it's more like a motivate the formula, because the formula for the moment of inertia is unusual looking, I think. Okay, so if I have this is really a like a washer on a string. Okay, so if we pretend it was like a ball on a string or a bead on a string. And what I'm going to do is I'm going to cause it to undergo an angular acceleration by applying a net torque to the object. Okay. And so what we're going to look at is, if we go in and think about our equations, so then what we have is we have our, Newton's second law. So we would have things like the net force equals the mass times the acceleration. And so then if we translate this, the net force should become our net torque. And we've learned a little bit how to calculate that. The acceleration should become the angular acceleration vector. And then what we're kind of looking for is, what takes the place of the mass. Okay. And so this is where we're going. And so what I'm going to do is I'm going to go in and take a look at this little washer, or might actually be like a tinker toy or something like that. But Then I'm going to apply a force to the washer to cause it to angularly accelerate. I'm going to hit it like this and it's going to spin. Okay. So, I come in and I hit it tangentially and it goes, around and around. So that's the thing that I want to kind of take a look at to try to see what this moment of inertia thing will look like as a formula. Okay. So we're going to have our object on a string like this. This will be our axis of rotation. And we're going to cause this object to undergo, an angular acceleration, cause it to, whirl around like so. Not such a great circle. So sorry about that. Okay. And so then what we're going to do is we're going to apply a force horizontally or tangentially to our object. And then that will cause the object to undergo an acceleration in that direction. Like so. Okay. And if we go in and look, then by our Newton's second law, we'll put that this, is the positive tangential direction. Okay. So if we look at our, Newton's second law, that force in that tangential direction is m times a tangential. Okay. So I'll have this force, so plus F tan equals m times plus a tan, like so. Okay. Now, if we go in and look, then this is our axis of rotation. For this particular force to cause an angular acceleration, then we needed to create a net torque. So here's my line of action. And then that shortest distance from the axis of rotation to the line of action, this is our lever arm. So we get is that the lever arm will be equal to this, radius of the circle, like so. Okay. And so to get the torque, we have that V is that lever arm times the force. So if we go in and we multiply both sides by this radius of the circle, then what we get is this is R times F tan equals R times M times that A tan. Well, R times F tan, this will be our torque due to that particular force. And if we go in and remember that A tan was equal to R alpha, and we put that in here, A tan is R alpha. And if we rearrange the pieces, then what I can get is this is M times R squared times alpha. So then here's my net torque is equal to something times alpha, and this something should be our moment of inertia. And so then what we get is that this kind of motivates why the formula looks like this. So what we have is that for particle, sometimes they'll call them a point mass. Okay. Then what we get is that our moment of inertia is going to be equal to the sum from 1 to n of mr squared. Okay. And so if I write out what this looks like, this will be m1 times r1 squared plus m2 times r2 squared. And you keep going until you run out of little particles. So mn is the last one times rn squared. Okay. And so this is our moment of inertia. This is the mass of whichever particle that is, the first one, the second one, the last one, you know. So this is the mass of the ith particle. And then this r is that distance from the axis of rotation to where the mass is. Okay. So very much like the lever arm concept. So this is our shortest perpendicular distance. From the axis of rotation to the wherever the particle is. The location of the particle. And when we look at our units, they're going to be mass units, which are kilograms, times, distance units squared. So kilograms times meters squared will be the units of these moments of inertia. Okay. Now, I'd like to do an example to show you how these things will go, but we're going to take a break. Okay. So I did the general motivation for the moment of inertia, that it's this angular counterpart of the mass, talks about the ability to resist changes in the angular motion, like big truck versus little car. And then I kind of tried to show why it looks like it's an mr squared kind of term, because I think that's really, really wonky if we don't do something with that. And I'd like to at least show an example with this